Welcome. In this video, we are going to talk through some questions from the 2021 and the 2017 AP Chemistry exam. And these are questions that are related to calorimetry and deltaH and the idea of energy per mole reaction and thinking about maybe stoichiometry and how coefficients are involved in that deltaH value that we want to consider. So we're going to talk through these. And so before you watch this video, make sure you have tried these problems on your own. You want to give yourself time to think about it. So feel free to pause the video at any point along the way. So this is the 2021 problem. This is question number 4. It's one of the short problems, meaning it tend to just be like 2 or 3 parts to it. So in this case, this has questions A, B, and C. So it's a 3-part question. And it's related to this right here, this reaction between iron and oxygen gas. It looks like a very exothermic reaction. This is the reaction that's used to warm up hand warmers. And so a student is mixing some iron with a catalyst and some sand in a container, and they measure the temperature of the mixture as the reaction proceeds. And we've got some data right here. So the first question asks us to calculate the amount of heat absorbed by the mixture from 0 to 4 minutes. So we're going to pay attention to this time marks here. So we're going from 0 to 4 minutes. So we notice the temperature is changing. And we're going to take the final minus the initial temperature. It looks like our temperature, increased by, what is that, 17.7 degrees Celsius. And if I know a temperature change in a mass, this sounds like a job for Q equals MC delta T. So we know the total mass of our sample is 15 grams. The specific heat of the sample is given, it's 0.72. So notice how this specific heat is relatively low compared to, we've done a lot of aqueous reactions where we use the specific heat of water, which is pretty high, but this is sand, it's got a much lower specific heat, 0.72. And then my temperature change is 17.7 degrees Celsius. If I stop and plug this in my calculator, it's 191.16. Sorry, not grams. What are my units? Okay, so one of my units is, notice how grams cancel out, Celsius cancels out. My units are joules. And I want to check to make sure I've written that with the right number of sig figs. So this mass has 3 sig figs. My temperature change has 3 sig figs. But my specific heat only has 2 sig figs. So I'm going to round my answer to 2 sig figs. So I would just write it as 190 joules. Or if I wanted to write that in kilojoules, I would write it as 0.19 kilojoules. Notice how I want to drop the final 0 when I do it this way. Because if I wrote 0.190, that would make it look like it had 3 sig figs. So I don't want to do that. I want to write it like this. And they didn't say if they need it in joules or kilojoules, so either one of these would be fine for reporting your answer. Just make sure you label it with units. Okay, so that is A. And then B says to calculate the mass of iron in grams that reacted in order to generate this amount of heat. And you might think to yourself, well, they told me the grams, it's 15 grams reacted. Oh, but wait, this was actually a mixture. 15 grams was a mixture of the iron, the catalyst, and the sand. So the mass of the iron is going to be something less than 15, and we don't know what it is. So, but what we do know is that when the iron reacted, it released 190 joules, or 0.19 kilojoules of energy. So let's look back at our equation and see what it tells us. Well, notice in this equation, we see a stoichiometric relationship here. So for every, this kilojoule per mole reaction means for every mole of reaction, which a mole of reaction is basically this reaction proceeding kind of as written with these coefficients. So this reaction involves 4 moles of iron and 3 moles of oxygen combining to make 2 moles of iron oxide. So when all this reacts, you will release 1,650 kilojoules of energy. And so I want to know what my iron to energy relationship is. So looking at this problem, I knowing this iron to energy relationship is the one that's going to be useful to me. So let's scroll back down and see here. We know that, let's think about what we know. We know we want to make 0.19 kilojoules of energy. Okay, that's the amount of heat we calculated in part A. And then also what we know is we know the relationship that for every 4 moles of iron, we release 1650 kilojoules of energy. So for every 4 moles of iron, we release 1650 kilojoules of energy. So I have a couple options. One is I can write out like a ratio. If you like this, I could say, well, for every 4 moles of iron, I release 1650 kilojoules of energy. So if I want to release 0.19 kilojoules of energy, how many moles of iron would I need? And I can rearrange and solve for X. Another way you can think about it is with dimensional analysis. So the value we're starting with is 0.19 kilojoules, and I want to convert kilojoules into moles of iron. So I would say that 1650 kilojoules are released for every 4 moles of iron that react. So that's another way of doing it. Also, you might be bothered by the lack of the negative sign. So if I want to, I could put negatives. I can acknowledge that in both cases we are releasing energy. So really both these numbers are negative. And when we like multiply this out, let me plug that in my calculator, 0.19 times 4 divided by 1650, you end up getting 0.012346 moles of iron, which we can write with scientific notation if we want to. We don't have to use scientific notation, but we can. So that's our moles of iron. And I want to know grams of iron. So I'm going to look up on the periodic table, and I'm going to use my molar mass of iron, and it's 55.85 grams per mole. So when I multiply that by 55.85, I get 0.026 grams of iron as my final answer. Just so you know, if you look at the scoring guidelines, they did a little bit of a different approach, which is the same general idea. So let me kind of scroll down here and show you what they did, what the scoring guidelines look like. So what they did is they said, okay, you want to make 0.19 kilojoules of energy, and they took that deltaH reaction value and said that's 1650 kilojoules per mole reaction. That's how it was written out there. So what they did is they did that conversion first, and they said, okay, for every 1 mole of reaction, that's 1650 kilojoules of energy that's being released. So they did that step first and found moles of reaction. And then notice down here, they did a second step that said, okay, every 1 mole of reaction uses up 4 moles of iron. The way I set it up is I basically just combined these 2 steps into one relationship and just said, oh, for every 4 moles of iron, there's 1650 kilojoules. So whichever way kind of works for you there. Another thing I want to point out here in the scoring guidelines is that notice how the answer is either 0.027 or 0.026, depending on whether you carried the decimals through in your calculator. And either way is fine. Both answers are accepted. Okay, then let's look at the part C here. So part C is, what if we use twice the iron as calculated in part B, but the same mass of sand? Compare the maximum temperature reached in the second experiment. So, let's say instead of, reacting 0.026 grams of iron, you reacted 0.052 grams of iron. The maximum temperature is going to be greater than, so make sure you answer the question, greater than. And as far as an argument, I may make an argument that there's a relationship between the, moles of iron and kilojoules of energy that are released. So if you increase the moles of iron that react, you're going to increase the amount of energy that is released in the reaction. And since it says we're using the same mass of sand, and you're thinking, Q equals mc delta T, if you're still using sand and it's still the same mass, these values are the same. So when you have more energy being applied, you're going to see a greater change in temperature. I know I wrote symbols instead of writing that in words. But that's how I would explain that type of problem. And if you scroll down and look at the answer key, they say, more iron. Here, I'll scroll down and show you. So if we look at these are the scoring guidelines. And this is put out by the College Board, and they always accept, a variety of answers. This is just one sample response. But the greater mass of iron means more reaction occurs, which means more thermal energy being transferred to the same mass of sand, giving you a greater maximum temperature. So key thing is that more moles means more energy released, but it's the same mass, so you got a greater temperature change. That's the big takeaway. Okay, so that is the 2021 problem. Now let's talk about the 2017. If you want to keep going with us, we can. So the 2017 problem, it is a calorimetry experiment. And notice that in this case, it's a calorimetry experiment where you have the reaction. It's not an aqueous reaction, right? The reaction is kind of occurring down here below, and it's transferring heat energy to the water. So your thermometer is going to be measuring the temperature of the water. You're going to be doing a combustion reaction down here. So this is your propanol that is going to combust. This combustion reaction is going to release heat energy and be absorbed by the water. And so what we're going to do is we're going to measure the temperature change and the mass of the water to figure out how much energy the water is absorbing. And then from that, we can figure out how much energy the combustion reaction is giving off. Okay. Okay, so we take a look at our data set down here. We're getting some info on the table. Notice how the temperature of the water increased. I guess it was kind of gave something away earlier when I said the, combustion reactions releasing energy. How we can tell that is because, look, the temperature of the water increases. So the water temperature is increasing. So it ends up at 51. It starts at 22.0. So your change in temperature of your water is 29.1 degrees Celsius. So notice how since the water's temperature increased, that means it absorbed energy, which tells us that the reaction releases energy. So we'll keep that in mind as we go forward here. All right, there we go. We've got the specific heat of water. We've got the mass of the water. So if we have temperature, data, mass, then that's a clue that we should use this equation, Q equals MC delta T, which remember is on our equation sheet. Whenever you're doing this type of calculation, always ask yourself, what mass should I use? So should I combine the masses or should I keep them separate? Well, if we look at the setup here in this reaction, notice how the water and the propanol are totally separate. Okay, they never come into contact. They're not in the same container. So the mass I should use is the mass of whatever I'm taking the temperature of, which is the water. So I should use the mass of just the water. So it's 125.00 grams. And then I'm using the specific heat of water, 4.18 joules per gram degree Celsius. Make sure you're labeling units here. And then my temperature change, 29.1. And if I stop and solve here, notice how grams cancel, Celsius cancels. If I plug this in my calculator exactly, I get 15,204.75 joules, but that's probably not the right sig figs. Okay, let's check sig figs. This number has 5 sig figs. This number has 3 sig figs. This number has 3 sig figs. So my answer should have 3 sig figs. So I'm going to write it like this, 15,200. So if there's no decimal, then these trailing zeros are not significant. But the question actually asked me to report it in kilojoules, and we know that 1 kilojoule is 1,000 joules. So I'm actually going to write this as 15.2 kilojoules. There we go. So that's my energy absorbed by the water. So now what I want to do is figure out how much energy would be released if a mole of propanol combusts. So let's go back and observe what we did here. So 15.2 kilojoules, that is the amount of energy released per 0.55 grams of propanol. And I better check the molar mass of propanol. So 1 mole of propanol, I'm going to look it up. I don't think the problem gives it to me, does it? No. Okay, so I'm going to use my periodic table, and add up those to get the molar mass of propanol. So the molar mass of propanol is 60.09 grams. So I reacted much less than a mole of propanol, right? So I want to figure out how much energy would be released if I reacted an entire mole of propanol. So let's figure out how many moles we reacted. So we only reacted 0.55 grams. So that's 0.55 grams of propanol. So let's figure out how many moles that is. So a mole of propanol, my handwriting's getting messy, weighs 60.09 grams. So that ends up being 0.0092 moles. This number has 2 sig figs in it because our mass has 2 sig figs in it. Okay, and I want to find the energy per every 1 mole is combusted. So basically what this question is asking me to find is find the kilojoules per mole of C3H7OH. So what I'm going to do is I'm going to take to find the energy per every 1 mole, here, let's set it up like a ratio. So I want to find how much energy is released when 1 mole reacts. What I observed is that when 0.0092 moles react, I released 15.2 kilojoules. So to find the energy per every 1 mole is, notice I just take this number and divide by this number. So 15.2 divided by 0.0092, that is going to give me the energy per mole. So when I plug that in my calculator, I get, I think, 1652 kilojoules per mole. That's too many sig figs, though. That has 4 sig figs. This number has 2 sig figs, and this number has 3 sig figs. So I need to round my final answer to 2 sig figs, which would be 1700 kilojoules per mole. Or if you want to write with scientific notation, you can say 1.7 times 10 to the third kilojoules per mole. So really this question is just asking us to find the energy per mole of propanol. Okay, and notice how this is a distinction. They didn't ask us to find the energy per mole reaction. That would actually be slightly different. If they asked us to find the energy per mole reaction, because this is energy per mole propanol, so let me label that one. If it asked me to find energy per mole reaction, I would have to take into account the fact that every 1 reaction involves 2 moles of propanol combusting. So let's do a little side note here off to the side. This is not what the question was asking us for, but if it had asked for energy per mole reaction instead of energy per mole propanol, then what I would need to do is I would need to take my number here. So it's 1700 kilojoules for every 1 mole of propanol. That was the answer we just found. That was the answer to the question. Boom. And then I would need to convert from moles of propanol to moles of reaction. And it looks like for every 1 reaction, let's scroll up and look again. For every 1 reaction, 2 propanols are combusted. So it's a 1-to-2 ratio here. So there's 2 moles of propanol for every 1 mole reaction. So to find the energy per mole reaction, it looks like I'd actually multiply this by 2. So that would actually be, this would be the energy per mole reaction. Yeah. Actually, I was just thinking another way you could think about it. And I am getting a little off. I'm getting beyond what the question's asking us for. Okay, but I just wanted to point out some other things. So we could say that if we were finding the energy, the deltaH for the reaction would be 3,400. That's the energy per mole reaction, right? And then notice how this question asked us to find the energy, and a reaction involves 2 moles of propanol combusting. The question had asked us to find the energy per every 1 mole of propanol combusting. So another way to think of it is we can think about those rules we use with Hess's law. So if I took this equation and divided everything by 2, I'm going to rewrite it down here below. That would be C3H7OH plus 9 halves of an oxygen. I know that's weird. 6 divided by 2 is 3. 8 divided by 2 is 4. So if I cut this reaction in half, the delta H value would cut in half. So notice how this was the answer to our question part B. So for 1 mole of propanol to combust releases 1700 kilojoules. For the reaction that was originally written, if the question had asked me to solve for that, then the delta H would be 3400. So I'm just trying to point out the relationship between like coefficients and this kilojoule value, and there you go. All right, so now let's look at the last question, which is basically an error analysis question here. So imagine that we have the same mass of water, same initial temperature, but you have a sample that's contaminated with water. So imagine, experiment 1 has down here, you've got your just pure propanol. So this down here is 100% propanol. That's experiment 1, and you're heating up your water up here. And then in experiment 2, you have the same scenario with the same amount of water, same initial temperature, that's all the same. But what's different in experiment 2 is your propanol is contaminated. So sometimes it helps me to apply a number to it. So like, let's say a propanol is contaminated with water. So now it's a mixture of propanol and water. So instead of it being 100% propanol, let's say it's 90% propanol. Okay. And in both scenarios, we still react 0.55 grams. Okay, so in reaction number 1, 0.55 grams of propanol combusts. Okay, it's going to release a certain amount of heat. In experiment 2, we got 0.55 grams reacting, but it's no longer pure propanol. It is a mixture of propanol and water. So we're still losing 0.55 grams of mass there, but it might be that some of this is actually just water down here evaporating. So if only 90% of your sample is propanol, that would mean that 90% of 0.55 grams, that would mean, like, for example, only 0.5 grams of propanol combusts. So in experiment 2, since your sample down here that you think is pure propanol, since it's actually contaminated with water, you are not reacting as much propanol as you thought. Okay, so what's happening over here in experiment 2 is not as much, fuel, your propanol, is combusting. And so if you have not as much propanol reacting, you're going to release less heat. So let's make sure I go back and am I answering the question? It's asking, would the final temperature in the beaker be greater than, less than, or equal to? Well, in this scenario, since I'm burning less propanol because my propanol is contaminated, that means I'm releasing less heat. And if I look at this relationship, if I release less heat, my temperature change is going to be smaller. So the answer to this question is less than. So because I'm combusting less propanol, releasing less heat, my temperature change is going to be less. So yeah, and that's it. So thanks for sticking with me. I know that was kind of long, but I wanted to spend time to kind of dig into some nuances with these questions. So I hope that helped.